Okay, let's move on. We have begun to discuss the molecular orbital theory in the last uh, class, and I told you that are three criteria that determine the degree of the covalent interaction. So the first one is the energy criterion, the second one was the overlap criterion, and the third one was the symmetry criterion. And the symmetry criterion gives a yes, no answer. So either the symmetry of two orbitals is right or it is wrong. If it's right, then we can construct molecular orbitals. If it's wrong, then we cannot construct molecular orbitals. So in the last class, we determined that right or wrong by inspection. However, as I told you at the end of the last class, this can be tricky, especially when the molecule becomes more complex. So for that reason, there is a more formal approach to determining right and wrong symmetries, which is the so-called symmetry adapted linear combination approach, which applies group theory in order to make that decision. So using that formalism less ambiguously, you can determine right and wrong symmetries of atomic orbitals, construct molecular orbitals. So that formalism applies a number of rules I would like to review briefly. So the first step is to determine the point group of the respective molecules, So you have to be aware of the symmetry of the molecule. So the next step is to define the coordinate system in a useful way. That doesn't mean that there's only one way to do it, but it should be a way so that basically you make your life as simple as possible with choice of the coordinate system. In the next step, you then do the actual symmetry adapted linear combination of atomic orbitals, also just abbreviated SALC. So what that means is that you determine what are the valence orbitals within your molecule. And then you first look at the ligands and look at the valence orbitals of the ligands. And then you determine, well, which ones are symmetrically and energetically equivalent, meaning that which ones are actually interexchangeable by the symmetry operations. So you combine these orbitals, these ligand orbitals, to form so-called ligand group orbitals. So the number of ligand group orbitals must always be the number of ligand atomic orbitals from which they have been constructed. So in the next step, you then determine the symmetry types of these ligand group orbitals. And after you've done that, you also determine the symmetry types of the central atom orbitals. So the next step is then that you combine ligand group orbitals and central atomic orbitals of the same symmetry type to form molecular orbitals. Okay, when they have the same symmetry type within the particular point group, then you know that their symmetries are right and you can combine them. If they have different symmetry types, you know that symmetries do not match up. They cannot be combined to form molecular orbitals. Okay, so again, the number of molecular orbitals formed and the number of atomic orbitals from which they have been constructed in the end of the process must be the same. That's always a good check whether you've done the process right. If there is a different number of molecular orbitals compared to the number of the atomic orbitals, then that's a sign that you must have done something wrong and you have to try to find some mistake. Okay, so this is the process in very general. Now let's apply this process to an example to get familiar with this. Let's look at the example of water, H2O. So first we would have to determine the point group of the water molecule by determining the symmetry elements and symmetry operations, and then determine what's the point group according to the symmetry elements and symmetry operations. Okay. So now the water molecule, it has a 2 axis here. It has actually 2 vertical mirror planes in addition to that, and of course it has the identity. So these symmetry elements and symmetry operations are associated with the point group C subscript 2V. This is here the Schoenflies formulation that we use because we are working with a molecule. Okay, so then we can next look at the coordinate system. So one way to define the coordinate system, a useful way, is to say that, well, our molecule, it lies in the xy, in the xz plane, and then our y-axis stands perpendicular to that plane. Okay, so for instance, x can point to the right and z can point to the top. That would be one useful way to do that. Okay, so now we have to be aware of the valence orbitals in that molecule. So looking at the hydrogen only has the 1s orbitals as the valence orbitals. The oxygen has the 2s and the 2p. So according to the rules we just discussed, we first need to look at the valence orbitals of the ligands. And according to the rules, we should combine the ligand orbitals that are interchangeable by this symmetry operations to form ligand group orbitals. Now the 2 1s orbitals are interchangeable. They're also symmetry equivalents. Certainly, we can combine these two to form ligand group orbitals. So now, how many ligand group orbitals will we expect? Well, because we combine 2 atomic orbitals, the 2 1s orbitals, we would expect 2 ligand group orbitals as the result. Okay, so what is the next step to do? We have to determine the symmetry types of the ligand group orbitals. So in order to do this, we first have to understand what is meant by symmetry type. So a symmetry type is associated with an irreducible representation within the character table for the respective point group. Okay, so the character tables are a product of group theory, and we can use these character tables that are available in books and literature in order to determine the symmetry types of these ligand group orbitals. So here you see the character table for the point group C2V, and you see that the point group symbol C2V is listed in the top left corner of the character table. So to the right of this point group symbol, there are the symmetry operations listed, the identity, the C2 operation, the first sigma V and the second sigma V. Okay, the first sigma V is defined as the xz plane, and the sigma V prime is defined as the sigma yz plane. Okay, so now you see here underneath C2V different symbols. Okay, so these different symbols represent different symmetry types, irreducible representations in that respective character table can have. Okay, so for instance, this A1 means that we have an irreducible representation with the symmetry type A1. and that irreducible representation would be defined by the characters in the respective line underneath the symbols for the symmetry operations. Okay, so this would refer to these four numbers here: 1 underneath E, 1 underneath C2, 1 underneath sigma, and 1 underneath sigma B prime. So essentially, these numbers basically say what the respective symmetry operations do with the coordinates in the respective point group. So actually, the character 1 means that nothing changes to the respective coordinates as we carry out the symmetry operation. So the coordinate actually you find now in the column behind these columns, in which you find the symmetry operations. So now, in the case of the symmetry type A1, in this irreducible section here, the coordinate is Z. Okay, so that means that essentially these four symmetry operations does nothing with coordinate Z when we carry out the symmetry operations. Okay, and that is associated with the symmetry type A subscript 1. Okay, so now, for example, you would find the coordinate X here in this row associated with the symmetry type B1. So for B1, the characters in the irreducible representation would be 1, -1, 1, -1. So these minus signs would say that they actually change the algebraic sign of any coordinate X as the symmetry operation is being carried out. So you see here the letter Y in the line for the irreducible representation with the symmetry type B2. So in this representation, you see we have the characters 1, -1, -1, 1. That means when we do the identity and sigma V prime, that does nothing to our coordinate Y. However, if we apply C2 or sigma V, then the algebraic sign of the coordinate Y changes. So the character table is actually more general. It tells you in general what the symmetry operations do with the mathematical function. So what applies to a coordinate also applies to a mathematical function, which is a linear function of the coordinates Z, X, and Y. Okay. You can also have, for instance, square functions. So you see that in this column here, square functions are being listed. Okay, so any square function, which would be a function of x squared, would have the symmetry type A1 in the point group C2V. Any mathematical function which is a product of x and y would, for instance, have the symmetry type A2 here. Okay? But regardless what the mathematical function is, you have that finite number of irreducible representations and the finite number of symmetry types attached to them. Okay, so this is in a very brief form what character tables are about. So now our task is to determine the irreducible representations of our ligand group orbitals. Okay, so remember our ligand group orbitals must also be mathematical functions because atomic orbitals are wave functions. Okay, and well, any ligand group orbital, any molecular molecular orbital is just a linear addition of two atomic orbitals, so therefore any ligand group orbital or molecular orbital is also a wave function, which can be described by a mathematical function. So for that reason, you can apply character tables also to wave functions and orbitals. All right, but now how do you find out, well, which symmetry types belong to our ligand group orbital in the point group C2V? So in order to do that, you have a method which is called the orbital swapping method, which gives you first the reducible representation of the LGOs. So a reducible representation is a sum of two or more irreducible representations. Okay, so that means a reducible representation has a sum of the characters of the irreducible representations. So for example, I could add up these two irreducible representations, B1 and B2, and then the respective reducible representation would have the characters, well, 1 plus 1 is 2, -1 plus -1 is -2, 1 plus -1 is 0, and -1 plus 1 is also 0. Okay? So now our formalism says that we first have to find the reducible representation, the sum of the irreducible representations, and then determine what are the irreducible representations the reducible representation is composed of. And you can do this by a fairly simple method, which is called the orbital swapping method. And using that method, you can determine for each symmetry operation, if the symmetry operation leaves the orbitals unchanged, and that means the atomic orbitals that we look at, the 1s orbitals of the hydrogen atoms, or if they are being swapped over. And if they're being unchanged, they're getting a character 1 for each orbital, and if they're getting swapped, they get a character of 0. And that determines the characters on your reducible representation. So now, when we look at the identity, because the identity never does anything, well, of course, our two orbitals are not getting swapped as we carry out our symmetry operation. Therefore, each 1s orbital gets the character 1, and the sum of that is 2. So that means that the first character in our reducible representation is 2. So now let's do the same for the C2 symmetry operation. So if we carry out the C2 symmetry operation, we actually rotate around that C2 axis, which stands here. And does that swap the orbitals? Yes, of course. It moves this orbital into that position, and it moves this orbital here over into that position. So therefore, both orbitals get the character 0, and 0 plus 0, well, that's overall 0. And that's now the character of our second, it's the second character of our reducible representation. Okay, now let's do this for the sigma xz plane. So now the sigma xz plane is, according to our definition, the plane which is the same as the plane of the molecule. So do the orbitals get swapped? The answer is actually no. And you see, actually, there's a little mistake on that slide. It says that the orbitals are getting swapped, but actually do not. Okay, so we have the plane in the plane of the molecule, and therefore the two orbitals stay at their position. So here it says correctly that therefore each of them gets the character of 1, and that sums up to 2 overall. So now to determine the last character of our reducible representation, we need to look at our second mirror plane. So this now stands perpendicular to the plane of the molecule, and this one moves this orbital to the right side and the right orbital to the left side. So both orbitals are getting changed. So again, here there's unfortunately a little mistake on the slide. So here the orbitals are getting changed. Therefore, the orbitals both get a character of 0, and that sums up to 0. So overall, our reducible representation is 2, 0, 2, 0. So now we have completed the first step. Our second step is now to determine what are the irreducible representations associated with that reducible representation. And for that, group theory also has a formula that we can simply apply here, which is called the so-called reduction formula. So the reduction formula gives you the number of irreducible representations of a given symmetry type. Okay, and that is exactly what we are looking for. So that number is equal to 1 of the order of the point group times the number of operations in the class, whereby class means a column associated with a symmetry operation, times the character of the reducible representation for that particular symmetry operation, times the character of the irreducible representation for that particular symmetry operation. And then we just sum up over all the symmetry operations R, and that gives us then the number of the irreducible representations for a particular class. So in the point group C2V, we have 4 different symmetry types, A1, A2, B1, and B2. So we can apply this formula here to all these different symmetry types to determine, well, how many Ligand group orbitals of a particular symmetry type do we have. Okay, so we can start, for instance, with the symmetry type A1 and apply that formula. So now, first we have to know what this term is, 1 of the order of the point group. Now, the order of the point group is simply the sum of all the symmetry operations in that point group. And you can read that from the character table. Okay, so we have 1 identity operation, 1 C2, 1 sigma V, and another sigma V, so that gives overall 4. Okay, so we have 1 over 4. It's this term here. Okay, so now we have to multiply the number of operations in the class for the first symmetry operation, which is E, times the character of the reducible representation times the character of the irreducible representation. So what is the number of operations in the class? Well, we would look at this column here and see, well, how many identity operations do we actually have? Well, of course, only 1. And therefore, that character is 1. So the character in the reducible representation underneath the identity, which we determined previously, is 2. So we have 1 times 2. And the character of the irreducible representation is now this character here in the row for A1 underneath E. You see that's also 1. So that's 1 times 2 times 1. Okay. So now I have to determine the same product also for the other symmetry operations. So we can look next at the C2 symmetry operation. Okay. Now, what's the number of symmetry operations in the class? Well, we only have 1 C2 symmetry operation, the C21. Okay, we rotate around 180 degrees. That's all we can do. If we rotate 2 times, then that's already producing the identity. So therefore, the character is again 1. So now the character of the reducible representation for C2 is previously determined, that is 0. We multiply 1 times 0, and then we multiply the character of the irreducible representation with that, and that's actually this character here, and that is 1. So that's 1 times 2 times 1. All right, next we have to look at the mirror planes. Okay, for sigma v in the xz plane, what is the number of symmetry operations? In the class, we have only one symmetry operation here. Okay, only one reflection operation associated with that mirror plane. Reflecting more often would just produce the identity. So therefore, again, the character here is 1. So what is the character of the reducible representation? Well, this is now this character here, which is 2. And last but not least, we need to look at the character of the irreducible representation, which is now the character within the line of A1 underneath sigma v, which is 1. So it's 1 times 2 times 1. Now let's look at sigma v prime. So number of operations in the class is obviously 1. Then the number of the reducible representation, well, that is this one here, that's 0. And the character of the irreducible representation, this is now this one here, which is 1. So we have 1 times 0 times 1. So now what does that give overall? So we have a quarter times 2 plus 0 plus 2 plus 0. So we overall have 1 over 4 times 4, and that's 1. So what does that mean? That means we have found our first ligand group orbital, and we can say that one of the 2 ligand group orbitals that we are looking for has the symmetry type A1. So now you can apply the same process also for the other symmetry types, A2, B1, and B2. So for A2, you would get the result 0. And that means that no ligand group orbital has that symmetry type. So for B1, you would get the result 1. And that means that the other ligand group orbital must have the symmetry type B1. And for B2, you get the value 0, meaning that no ligand group orbital has the symmetry type B2. Okay. Note that you always have to get integer values for these numbers. If you don't get integer values for your calculations, actually that means that something must be wrong with your calculation, and you have to find the mistake. Okay. So overall, we can say that our reduced representation is composed of 1A1 irreduced representation and B1 irreducible operation, irreducible representation. Okay, so this is an important step forward because we know now the symmetry types of our ligand group orbitals. So now next we need to look at our central atom orbitals. So we said that the central atom orbitals of the oxygen are the 2s and the 2p orbitals. So we can find their symmetry types very easily directly from the character table. Okay. So the 2pz orbital, as the name says, is a linear function of z. For that reason, it has the symmetry type of a linear function of z, which we can find here in this column by the symbol z within the character table. That means that our 2pz orbital is a 1 symmetry. So we find the letter x here in the row for the symmetry type B1, that means that our 2px orbital has B1 symmetry, and we find the letter Y here for the B2 symmetry type, and that means that the 2py molecule, sorry, the 2py orbital, not molecule, has B2 symmetry. So now what about the 2s? The 2s orbital is not the function of any coordinate. For that reason, it's spherical, and due to the spherical nature of our orbital, it has always the totally symmetric symmetry type, and that's always the symmetry type in which all characters are 1. In a character table, this symmetry type is always listed first, so in this case it's associated with the symmetry type A1. So that means that our 2s orbital has the symmetry type A1. Okay, so now we can go to the next step and combine central atom orbitals with ligand group orbitals that have the same symmetry type. Okay, because we know that when they have the same symmetry type, they have this correct symmetry to be combined to form molecular orbitals. Okay, so now for the symmetry type A1, we determined that for the central atom orbitals, the 2s and the 2pz orbital has that symmetry type. We also determined that one of the 3 ligand group orbitals has that symmetry type. Therefore, we can combine these 3 to form molecular orbitals that have now the same symmetry type, namely A1. So the number of molecular orbitals must be equal to the number of orbitals from which they have been constructed, which in this case 3. So therefore we have 3 molecular orbitals as a result. So now for the symmetry type A2, we realize that there's no central atom orbital, nor is there a ligand group orbital of that symmetry type. So certainly we will not form any molecular orbital of that symmetry type. Now for the B1 symmetry type, we determined that the 2px orbital has that symmetry type, and our second ligand group orbital has that symmetry type. So that means that we can combine these two to form molecular orbitals. Overall, we will find 2 molecular orbitals of that symmetry type. So last but not least, we have symmetry type B2 to consider. The 2py orbital has that symmetry type, but there is no ligand group orbital that has that symmetry type. And that means that our 2py orbital doesn't find a partner to form molecular orbitals. It has to remain non-bonding. Okay? So now you see that this is the same result that we previously found by inspection. Okay? Remember the last class when we tried to combine the 2py orbital with the 1s orbitals. Whatever we did, the bonding in the anti-bonding interactions cancelled out. Okay? So here we arrive at the same result, but we arrive at this result using the group theoretical formalism, which saves us the inspection work. It makes our result independent from inspection work, which could be flaw 4. So now with this information, we can construct a molecular orbital diagram, which you see here. So in a molecular orbital diagram, you usually plot the atomic orbitals on the left-hand side of our molecular orbital diagram according to energy. So the 2s orbital would have a lower energy than the 3 2p orbitals. These 3p orbitals are here. So that small energy difference does not realize a real energy difference. It's just um, a result of the necessity to draw 3 different lines. So then we have 2 ligand group orbitals to consider, which we write on the right-hand side. We can write them also according to energy. You see that the LgO1 has a somewhat smaller energy here than the LgO2. That is, because if we inspected the two more closely, we would find that the first one has no node, while the second one has actually 1 node. Okay, so the first one actually represents 2 1s orbitals of the same algebraic sign to be combined, while LgO2 represents the combination of the 2 1s orbitals having opposite algebraic sign. So that creates a node, and that means that the LgO2 has a somewhat higher energy than the LgO1. But we have to keep in mind here that these LGOs are just mathematical products that are intermediates, so they don't have really a physical reality. So for that reason, sometimes they're also just written having the same energies. The energy differences are typically very small anyhow, because the 2s orbitals are fairly far apart, so the overlap is very small. Yeah, and therefore any bonding or bonding interactions between them don't influence the energy much anyway. Okay, but now the important thing is that we combine orbitals of the same symmetry type to form molecular orbitals. So we can again start with A1. So we previously determined that we can form 3 molecular orbitals. So when we combine 3 orbitals to form molecular orbitals, as a rule of thumb, we can say that 1 will be bonding and 1 will be anti-bonding, and the third one will be of intermediate energy and will be approximately non-bonding. Could be slightly bonding also, or inter-bonding. We can't determine that by the qualitative construction of our molecular orbital diagram. Of course, you could compute exactly also the energies and the orbitals. That would give you additional information, but we will construct only qualitative molecular orbital diagrams here. So that will give you the following. You see actually here our bonding molecular orbital. So the bonding molecular orbital must be lower in energy than the lowest energy atomic orbital from which it has been made. So this would be here, this 2s. So we write it actually below that 2s. Okay, then we have here the respective anti-bonding orbital. So that has to be energetically higher than the highest A1 atomic orbital. Okay, so that would be one of the 2 p's here. Okay, and then the third one is about energetically halfway between the anti-bonding one and the bonding one. You see it actually here. Okay, so then we just label these according to energies. So that makes this one the 1A1, that one the 2A1, and that one the 3A1. Okay, so now we connect these orbitals with the atomic orbitals and ligand group orbitals they have been made from. Okay, so those with the same symmetry types. Okay, so we have here these dotted lines, and here these dotted lines. Actually, this has been omitted. Okay, this line has been omitted because the large energy difference between the 3A1 and the 2s, they actually also have the same symmetry. So there is therefore a small contribution of that 2s to this 3A1 also, because of the large energy difference. Sometimes in the literature, then the dotted lines are not drawn One could, however, also draw a dotted line between this orbital here and this orbital here because they're the same symmetry types. Okay, so see that this A1 has contributions from, well, the 2p, the 2s, and LGO1. So this 1A1 has contributions from the 2s, 1, 2p, and LGO1. All right, so next you can go to the next symmetry type, for instance, B1. We know that we can combine the 2px, which has the B1 symmetry, with LGO2, which has also B1 symmetry. So that gives you a bonding molecular orbital, which is shown here, and an anti-bonding molecular orbital, which is shown here. Okay, we again connect these two molecular orbitals by dotted lines with the atomic orbitals or ligand group orbitals from which they have been constructed. Here, these dotted lines. Okay, so last but not least, we have to consider the, yes, Thomas.
Just curious there, how come the B1s are being drawn to B2 molecular orbitals?
Oh, I'm sorry, that is actually again a typo. Yeah, I haven't seen that. So this actually has to be a 1. Okay, let this be a 1. Can correct that on the slide.
Okay, all right, thank you.
Thank you for that comment. Yeah, I haven't seen this. So now the last one, the B2, has to remain non-bonding. And of course, this has to be then a B2 here, or not a B1. So these are mixed up. Yeah, good comment. Okay, so last but not least, we need to fill in our electrons. So we have to be aware how many electrons we have. So oxygen has 6 valence electrons. So hydrogen has 1 electron each. Overall, we have therefore 2. So 6 plus 2, that gives 8. And we can fill the 8 electrons into the molecular orbitals we have constructed according to energy. So that fills you this 1A1. The 1B1 is filled. Then the 2A1 is filled. And the 1B2 is also filled. Okay? So these two remain empty. So this one here is the highest occupied molecular orbital. So this one here is your lowest unoccupied molecular orbital. Okay? So you see you have 2 bonding molecular orbitals with 4 electrons. In the valence bond picture, you could say, well, these are the 4 electrons that make your 2 covalent oxygen-hydrogen bonds. And then you have 4 approximately non-bonding electrons here, which in the valence bond picture would represent your electron lone pairs of the oxygen atoms. Okay, see, however, in your molecular orbital picture, you get more information. In the valence bond picture, all the 4 bonding electrons would come out equal. You see, that's not the case in the molecular orbital picture. Also, electron lone pairs would be indistinguishable in the simple valence bond picture, while here you see that there are 2 pairs of electrons that are not energetically equal. So with the help of a molecular orbital diagram, you can get a refined picture of the bonding. However, that comes at the expense of more work. Constructing a molecular orbital, certainly more work than just drawing an H2O molecules with 2 electron lone pairs and 2 bonding pairs of electrons. All right, now let us do one more example. Before we go to special extended solids, let's do the molecule BH3, which will introduce the concept of degenerated orbitals, which is something which we should discuss. So the method for determining the molecular orbitals is basically the same. So first you have to be aware what is your point group. Yeah, and the point group for BH3 would be D3H. Okay, then you have to define your coordinate system. So we have here a planar molecule. So one useful way to define the coordinate system is to have the XY plane to be in the plane with a molecule. X would point to the right, Y would point to the top, and one of the three boron hydrogen bonds would contain the Y-axis. All right, so the next step is to decide what are the valence orbitals. So for the boron, that's the 2p and the 2s. For the hydrogen, again, that's the 1s. So the 1s would again form the ligand group orbitals, but now we would have 3 1s orbitals. So how many ligand group orbitals would that therefore give? Somebody say? I see an answer in the chat. 3, that's correct. Very good. So now the next step is to determine the number of the symmetry types. Now right now, again, my forward button does not move anymore. It's a fact we had before. Still unexplained. Sometimes it still freezes for an unknown reason. Let's see if I can move this way. Oh no, here. All right. So now we determine the reducible representation of the ligand group orbitals. So we can apply the orbital swapping method. Now for the identity, these 3 orbitals never swap, right? So all of them get the character 1. So therefore the first character is 3. So you can see here. So now for the C3 axis, or for the C3 symmetry operations, we have here now a C3 axis standing perpendicular to the plane of the molecule, going to the boron atom here. We realize as we rotate by 120 degrees, yeah, we move, orbital 1, position of orbital 3 to orbital 2, and orbital 2 in position of orbital 1. So all of them change the position. Therefore, each of them gets the character 0, and the sum of that is again 0. All right, then we have actually C2 axes. We have actually 3 of them. So we have one of them going through this BH bond, the second one going through that BH bond, and the third one going through that BH bond. So now, as we carry out the symmetry operations, we realize that we always swap up 2 of the 3 orbitals. So for example, when we use this C2, we swap up orbitals 2 and 3, but orbital 1 just remains in its position. So for that reason, 2 of them get the character 0, and 1 of them get the character 1, so therefore overall the character is 1. So now we also have S3 rotation reflection operations to consider. Two of them, the S31 and the S35. We could use either of them to determine what is the character of the reducible representation. So regardless, we have to always rotate first by 120 degrees. In that rotation step, like the C3 rotation, will of course move the atoms around. Therefore, all of them will get the character 0 and the overall character is 0. All right, then we have 3 sigma V mirror planes to consider. So they actually contain the BH bond axes. So one stands here, one stands here, and the third one stands here. Okay, so therefore, when we carry out the symmetry operation, then the atoms, the orbitals 2 or 3, for instance, get swapped up, yeah, while the atom 1 remains in its position. So therefore, again, one orbital gets the character 1, and the other 2 get the character 0. That sums up to 1 plus 0 plus 0 gives 1. So finally, we have to consider this sigma H mirror plane, which lies in the plane of the molecule. So now, of course, none of the 3 atoms change their position. So therefore, each of them gets the character 1, which gives you overall 3. So this now is the overall reducible representation, from which in the next step we would need to determine the irreducible representations. But I see our time is over, and therefore we are going to stop now.